we've seen what it looks like to have a force on a wire, and we've done some examples of what it looks like to have a force on a moving charge. So now I want to do a force on a wire and just run through an example or two. So let's do this first. I'm going to have sort of the simple case first. This wire can keep moving for a while. We'll give it a current of 2 amps, a length like this of maybe 40 centimeters, and we'll stick a magnetic field into the screen. Give that a field of half a Tesla, which is a pretty big field. So if I want to find this force, I'm going to say the force on this segment of wire is going to be magnitude force, just I, L, B, times the sine of the angle between I and B. I know I isn't exactly a vector, but it's a direction of current, and that's what I've got. So I'll plug these in. 2 amps. I have 0.40 meters because we want to be in meters. I'm going to go half a Tesla, and these are perpendicular to each other. My current is in the screen, or in the plane of the screen. The B field is perpendicular to that screen, so the sine of my angle here, this is going to be equals 1. 2 times 0.5 is 1, times 0.4 is 0.4, so I'm going to get 0.4 newtons. That is my force. And the direction of my force, I have a current going to the right, a B field going into the screen, so this is going to feel a force upward. I want to also do one where things aren't quite as clean as this. Maybe I have a current going, let's keep our current exactly the same, actually. We're going to say our I is 2 amps, and we're going to have a region where the B field looks like this. And this is really about the only thing you have to be careful of is which angle is given. So this B field is making an angle right here with the vertical of 30, let's go 60 degrees. It looks more like a 60. We'll keep the B field at half a Tesla, and we're going to keep the wire at 40 centimeters. So all we're doing is rotating our B field a little bit, but that's enough to just make a little bit different of a problem. So I'm going to do the same thing, but now my B field and my current are no longer perpendicular to each other, so I need to make them perpendicular. I'm going to split my B field into 2 components. One component that goes this way. This is my B perpendicular. One component that goes this way, and this is my B parallel. My B parallel does not matter as far as this stuff goes, so my B perpendicular is the one that I want, and in this case that's going to be a B times cosine of theta. Back here I said sine of the angle, but that was the angle between the current and the magnetic field. The angle between the current and the magnetic field is here. So if this is 60 degrees, this is going to be 30 degrees, and the sine of 30 degrees is going to be the same as doing the cosine of 60 degrees. So instead of looking at this as a ILB sine theta, I want to look at this as an ILB perpendicular, and that gets the job done too. So now my force magnitude is the current times the length times the B field times the cosine of 60 degrees. So I'm going to get 2 amps, 40 centimeters, B field half a Tesla, times the cosine of 60 degrees. Cosine of 60 degrees is a half. 2 times half is 1, times a half is a half, times 0.4 is 0.2 newtons is my force. I didn't care about my parallel component, so really I'm only worried about my perpendicular component. The direction is the same as it was last time, so I'm going to get a force that points, again, upward. And that's it. That's how I'm going to use my magnetic field and my wires to be able to get some kind of a force.